Hey everybody, I'm Igor. I'm from Rockset, and I'm here to talk about schemaless SQL. So before we start, let me tell you something about Rockset, where I work at, and myself. So Rockset is a search and analytics engine, and our goal is to build, make it very easy for you to build data-driven applications. We are a Series A startup based in San Mateo, California, and we are backed by Greylock Partners and Sequoia. Before Rockset, myself, I was at Facebook as a software engineer working on two projects, RocksDB and GraphQL during my time there. In my talk today, first I would like to introduce the concept of hardware and people efficiency, talk about how these two contrast and what I mean when I say those two. And then I will talk about how we at Rockset are designing systems for people efficiency. And there are three technologies that we use, and then I will go into some technical details, hope you enjoy that. Which is Schemaless SQL, converged indexing, and serverless architecture. So what is hardware efficiency? The other day I wanted to know which database is the fastest in the world, and I googled the world's fastest database, and apparently all of them are. And I actually have one more slide. There's many more. And when you say I'm building the world's fastest database, what I hear is you're making it hardware efficient. You're making sure that for my fixed workload that I have, I can use less hardware. I can spend less on hardware. So hardware efficiency is how much hardware do I need, and faster databases usually mean I am more hardware efficient. And it's very important to be hardware efficient, but my point I would like to make is that it's not the only thing that matters. What also matters is people efficiency. And if hardware efficiency is how much hardware do I need for a particular workload, then people efficiency is how many people do I need to get a job done or to complete a project. Or in the other way to say that is how much time do I need, how much overhead do I have to spend to deal with particular tools and to get some insights from datasets that I have. And there are a couple of ways where people efficiency breaks down in today's world and in today's data systems. The first way is, hey, my query is slow. And then the usual answers to that is, hey, did you build an index? What's your partition key? What's your buffer size? You have these 10 configuration parameters. Have you looked at tuning those? And in the end, maybe you should even hire a DBA to figure this all out for you. The second example, and it's a big one, is organizational friction. If you remember before cloud, if you're an application developer and an enterprise company, before you were able to build your applications, you had to go to your provisioning department and ask for 10 machines. And then they say, okay, here are some forms, fill that out, we'll talk to VP, we'll see if we can get you those 10 machines. And then between your idea for the application and the day when your application was actually running production, it could take 3 months of waiting for hardware. Thankfully, in the cloud era, you have AWS console, you go there, you maybe even have Kubernetes, you just deploy your application, and it just all runs on the hardware you can get from AWS. However, we still have this concept of data scientists being blocked on data engineers. For example, data scientists discovers a new data set they would like to explore, visualize, maybe like try to see if there are some insights out there. But if the data set is very big, they have to go talk to data engineers and ask them, hey, can you please set up my Spark cluster so I can analyze this data? Or can you do some ETL processing for me to actually see what's in the data set? And usually data scientists sometimes just say, hey, this data set is not worth it for me to go talk to data engineers. They're very busy with my more critical piece of projects. And then obviously pipelines. I'm pretty sure I'm not the first person using this XKCD comic in this conference, but I'll give you some time to read through it. Pipelines are our favorite thing to hate, and they are usually the reasons why also people efficiency breaks down. When you have pipelines, you have to monitor them. They break, schema changes, they break, and you just don't have data for that month or for that day, and it's usually very bad. And when I contrast hardware and people efficiency, what I usually see is that people or organizations spend less money on hardware than they spend on people. And then if you increase hardware efficiency, your organization will spend less money. That's great. But if you increase people efficiency, if you make sure and if you focus on reducing the amount of time people have to spend on mundane tasks, maintaining pipelines, for example, and you can increase their time they have in exploring different data sets and getting this creative spark, creative insight, this is overall a great win, and you will not spend less money on people, but you will instead increase creativity and actually add huge value to your business potentially. In the second part of the talk, I want to explore how Rockset designs systems for people efficiency, sometimes at the cost of hardware efficiency even. Let me tell you a little bit more about Rockset. As I said before, we are a search analytics engine, and what we're building is the shortest path from data to applications. And to think of Rockset as a tool, you can think of it as you can connect to existing data streams or data sources. It can be also real time. And then Rockset ingests those data sources into our own internal system, and then you can execute very fast queries on it. Now, how would we choose a query language? Obviously, in today's world, if you're building a data system and you want to expose it to your customers, you want to use SQL, because SQL in a way maximizes usefulness of your data system. There's a lot of people who understand SQL, and there are a lot of tools that work with SQL and let you query, drill down, and visualize your data sets. So SQL is the most obvious choice. But SQL has one big issue, which is, let's say you have existing data sources. Let's say you're a data scientist and you want to explore, let's say, Twitter data, and you want to explore some data that lives in the data lake. You want to explore some sensor data. You want to connect all of these together. SQL is great, but first you have to define a schema. And then you have sensor data. It's a third-party provider. They have a firmware update, and now the data that's coming in doesn't conform to your schema. Now you don't have the data anymore. You have to go talk to data engineers, and this whole system is broken. So what we see is that SQL schema is a very big drag on people efficiency, because data is usually messy. It doesn't conform to one schema, and then you have to build very complex ETL jobs to actually get data from your source to your destination that has to have a schema to query it efficiently. What we do at Rockset is we decided to use a SQL but not have a schema, and we call this schemaless SQL. What this allows us to do is allows us to ingest any data set you might have without any blockers. You just point us to a data set, whatever format it's in. Because we don't have a schema, we can just pull it in and ingest it into Rockset. However, we still build a smart schema. And now this is kind of a strange concept to understand, but we show the customer of what is the schema in the data set they ingest into Rockset, but in the code, we actually never use that. People sometimes ask me, how do you, optimize your SQL queries? We do not use a SQL schema as a concept in our code, but there is a specific query you can run to actually see how your data set looks like in Rockset. And now we call this smart schema, and if you download the slides later, you can see this slide, the link at the bottom of the slide where you can learn more about smart schema. And when we talk to data scientists that use Rockset, what they say, I'm finally independent. I have my data set. I don't have to go talk to data engineer. I can just ingest it into Rockset and explore it a couple seconds later, or basically immediately. And this is a huge win for them in terms of productivity, and this is what we talk about when we talk about people efficiency. However, obviously, if you don't have a schema, you will lose something on performance. So let's now go into technical details of how we actually solve performance overheads and what is the performance overhead of not having the schema versus having a strict schema. So how do we tolerate this hardware efficiency loss? And the first obvious part is storage. If you had the strict schema in this first row on the slide, you have the schema where the name is a string and age is an integer. Then when you encode the data set, you know exactly how the data set looks like. You don't have to encode what's the type of the field. You know John is a string and 35 is an integer, and using the schema that's strictly defined, you know exactly that John is a name and then 35 is an age. In the first version of Rockset schemaless implementation, what we did is we don't have a schema. So instead, in every single row in the database, we have to encode both the field name for each field, the field type, string, and the field value. So in this case, we have name, which is a string, and it's a John. And then we have age, which is an integer, in 35. So if you think about it, if every single one of your records has a name in it, and you have billion records, we repeat name, string, in our data set billion times. And that's obviously not very efficient. However, at some point, we decided to do this technique called field interning. And what I mean by field interning is we maintain a map between field names and IDs. And if the document comes into Rockset and we see a field name that we've never seen before, we add it to the map, assign it a unique ID, and then in the data itself, we do not have to store a field name. We only store field ID. So now instead of very long field names, we store integers, and I think this saved, about 30% of storage on disk that we used. So even though we still have to encode types, so we still have to say field ID 0 is a string John, field ID 1 is an integer 35, we still have a huge win by not having to store field names. The second piece where we lose out on hardware efficiency is query execution performance. And here what I'm talking about is when you execute the query, you load some data from disk and you put in this in-memory format. And then this in-memory format, this in-memory blob, travels through the SQL operators to actually compute the results of the query. You can go through aggregators, joins, and so on. And if you have the strict schema, you know exactly what types you're expecting, and your in-memory representation can be very, very efficient. So in this example, again, on the first row, we see how in-memory representation looks like within strict schema. We see we have 2 columns here and 5 rows. First column is all integers, and second column is all strings, and then we can just encode those in memory as vector of integers, just a flat array, and that can be done, and you can do processing on that very, very efficiently. In naive schemaless world, though, in the second row, what you have is you cannot have vector of integers because you do not know that all of them are integers, but you have vector of some type that's generic. And then inside of this generic type, you have the field tag. You say this is an integer, it's 1. This is an integer, it's 10. This is an integer, it's 7, and so on. And the same thing is true for the second column, where you have mixed types. So you have this is a string, it's an A, and some of them, this is an integer, and it's an integer. What you have when you pass this blob into your SQL operators is for every single element, you have this type dispatch. You have to check, is this an integer? Then execute this function. If it's a string, execute that function. And if you do this 1 billion times over, it's very, very slow. It kills your CPU cache. So instead, what we did is we have this technique called type hoisting. And what type hoisting does is as we're building this block, we are remembering, are all values in this column of the same type? If they are, then we encode this information in the header of the blob or of the page, and then encode all the fields for that column efficiently. So in this case, we can see that the first column, we have everything is an integer. So we encode I, as this is an integer in the header, and then everything else just is a very efficient vector of integers. And the second column, because we have mixed types, we say this is still a mixed type. So I look in line for the information about types. And now, if you actually have some implicit schema, if all of your field type, for a particular field type, all types are the same, you can still have this efficient query execution. But if your fields are mixed, it still works, it's still okay, it's just a little bit slower. In conclusion for this, schemaless SQL allows us to provide a superior user experience. If you have a data set, you can ingest it into Rockset, it all just works. We do lose out on hardware efficiency, but there are techniques we use to actually make this overhead smaller. We use field interning to reduce storage overhead, and then we use type hoisting to reduce query execution speed. The second technique I want to talk about is converged indexing. Converged indexing is Rockset's solution to the problem of query slow because I'm missing an index. So what's our solution? Index all the fields. Madness, right? Before I talk a little bit more about technically what is converged indexing, I want to talk a little bit about background on columnar storage and search indexing. How many of you are familiar with columnar storage? Okay, so I can go a little bit faster over the next couple of slides. So columnar storage, as opposed to row storage, is where I store data such that I store each column separately. And what this allows me to do is it allows me to compress the column values very well, because column values are usually similar to each other, and similar values compress better. And then when I'm executing the queries, I only can fetch columns that the query needs, even though my table can have many, many columns. If my query is touching only a couple, I can execute that very, very efficiently. And some examples of systems that use columnar storage is Vertica, Amazon Redshift, and BigQuery, which I'm sure most of you have heard about. Now, this is an example of how I would encode 2 documents in columnar store. Let's say I have 2 documents, document 0 with fields name, interests, and last active, and same thing with document 1. On the right-hand side, you can see how would this columnar store representation of these 2 documents look like. Obviously, we want to store each column separately. So for column name, we would store document ID 0, and the value is Igor. Document ID 1, and the value is Juba. The same thing is true for interests and last active. Advantages of columnar storage is that it's very, very cost effective. As I said before, the compression ratios are great, which means I get to save money. It also works very well for narrow queries and white tables. So if your table has a lot of columns and you're only querying a couple of columns, it works extremely well. And then the execution of columnar store is usually scan-based. You need to scan through the entire data set. You don't actually have an index. And as such, it works very well for analytical queries that have to scan the entire data set. However, on the disadvantages side, most columnar stores out there have very high write latency. What that means is when you insert data into your columnar store, it takes a couple seconds, maybe even a couple minutes, to actually reflect that change in your queries. As well, because the queries are all scan-based, your read latency, minimum you can achieve, is very high. It's usually a couple seconds, sometimes even a couple minutes. And if your minimum read latency is a couple seconds, you cannot put columnar store in an online application. It's not suitable for online applications, and people usually don't use it that way. On the other side, we have search indexing. In search indexing, such systems such as Elasticsearch, Solr, which are both based on Lucene, for each value, you store a list of documents that contain that value in a data structure called posting lists. And what search indexing allows you to do is if you have a particular predicate, you can quickly retrieve a list of document IDs that match that predicate. Let's go back to our original two documents. We have document 0, document 1 again. On the right-hand side, you can see how would encoding of those documents in search indexing look like. So we still have each column separately, but now we basically flip the document ID and the document value. So now instead of storing 0 maps to Igor, you say Igor maps to 0, and then Juba maps to 1. And then in interests, you see databases maps to document 0, index 0, it's an array, and also document 1, index 1. And so if you want to learn about who's interested in databases, you can quickly look with the search indexing. The advantages are, if you have highly selective predicates and highly selective queries that touch only some small portion of your data set, it can be very, very fast, and as such execute very low latency queries, and it's suitable for online applications. Elasticsearch, Google Search, all others are used in online applications where some customer is waiting for your result. However, people usually don't run analytical queries on search datasets. You don't want to do that. It's less efficient than if you used pure columnar store. And converged indexing, it's probably not a surprise. It's combining columnar and search indexes in the same system. And to present converged indexing, it's important to understand the key value store abstraction we build it on. So key value store abstraction, you can think of it as it's something that you can insert key value pairs into. You can retrieve a value for a particular key, and you can also do range queries on a sorted view of the data set. And we use RocksDB for that purpose in our case. But converged indexing can be built on any sort of key value store that presents your data in sorted order. That's important. Each document that comes in to Rockset or any other converged indexing system maps to many key value pairs. And to explore, let's go back to our document 0, document 1, but we'll make it a little bit simpler now, where we only care about name field, and we have Igor and Juba. On the right-hand side, you can see how those two documents would be encoded in a key value format in converged indexing system. So what we have is we first insert the document into row store. And in row store, the first component of the row store key is document ID, and the second component is the column name. So in this case, you can see document ID 0, name, and then value is Igor. And so what you can see here is if I want to fetch one document, I can do it quickly with the row store because I store all the values for a particular document close together because document ID is the first component of my key. I can just find all the keys that are prefix r.0, and I find all the values for a particular document. Then I have a column store where I flip the document ID and the column name. So now column name is the first component of the key, and the document ID is the second component of the key. And for my operation saying, find me all values for a particular column store is the fastest thing we can do. I can just find all keys with prefix c.name and find all names in our dataset. And we store column values close together, so it's very similar to existing column store. And then for search index, document ID goes to the final place in the key. So my key starts with column name, then there's a column value, and then finally a document ID is at the end. And if I want to find, for example, all documents where name is equal to Juba, I go into the key value store and I look for s.name.juba prefix. And once I find that, I find all the documents for which name is equal to Juba. Make sense so far? Any questions? I'm just going a little bit technical, but I hope you like it. So the question was, does it reduce speed when we are writing? Because now every document, it's not actually 3 times, because for every field in the document, we produce 3 key value pairs. So it's 3 times number of fields in the document. So now, when we do queries, I can do fast analytical queries and fast search queries. And then the optimizer picks between the column store or search index based on the query. So for example, if I had a query where for search logs, let's say Google search logs, I want to find out who searched for data council within locale equals English, my optimizer would say, okay, this is a query with very highly selective filter. I'm going to use a search index. And this query is going to be fast and very low latency because it's going to use a search index. And then in the same system, if I ask for, find me frequency of keywords, and let's say sort by the frequency, in this case, the optimizer will pick columnar store. And because we use columnar store, we will only actually fetch the values for keyword. We will not fetch any other values for those documents. So this is also going to be a very efficient query by using columnar store. And then on the writes, the question before was, because one document writes results in many key value store writes, how do we actually make sure that this is not too costly? And what we do is we use write optimized key value store, which is RocksDB. How many of you have heard of RocksDB before? Okay, quite a few, good number. So a little bit background on RocksDB and why do we call it it's a write optimized key value store. So RocksDB utilizes this technique called log structure merge trees, where all the keys that are inserted into RocksDB are first reside in this in-memory write buffer that we call memtable. Only when the memtable is full, we take the whole memtable and flush it to disk. And so you think about what happens is you have a lot of random writes, but you're turning them into sequential writes on storage. And as you're turning them into sequential writes, you can also compress it very well. And this is why we call it write optimized key value store. And then once you have a lot of files on storage, you also have background compaction, which takes those files and merges them together. One thing that's important to remember about RocksDB, that the RocksDB's files on disk are immutable. As soon as you write them, you never change it again. The only thing you do is you compact it with others and then produce new files. And this will become important later on. To conclude, converged indexing gives us fast queries out of the box. And it also supports real-time index writes. So previously I said that columnar stores are not great when it comes to write latencies. Because we use a key value store for our columnar store, we can execute real-time index writes. When you insert a document to Rockset, it appears in your index, usually a couple hundred milliseconds later. And let's see trade-offs between converged indexing and not doing that. The trade-off is more efficient is database configuration, and we have more efficient queries. On the less efficient side, obviously we use more storage than the traditional solutions, and our writes are heavier. But if you think about it, both storage and writes are hardware efficiency. We can spend more money on hardware. And what's more efficient here is database configuration, something people have been dealing with for many, many years, where how do I build the perfect index? You don't have to. All the indexes are already built. And overhead of dealing with the tool is reduced. And then your queries are also faster, which is you're waiting for the, your analyst or your customer is waiting for the query to complete, so you want that to be as fast as possible. And in my mind, this is win. This is a win on people efficiency, and you lose some hardware efficiency, but you actually care more about people efficiency. In this case, it's a win. And then finally, we have serverless architecture. And serverless architecture is probably obvious to all of us that it's a giant improvement when it comes to designing people-efficient systems. Rockset is delivered as a cloud service, which means you don't have to manage any hardware. You as a customer just use Rockset through the REST API, and that's it. There's no hardware to manage. However, in the serverless architecture, what's very important is to produce seamless autoscale. If I'm not managing hardware, then what happens if my load increases? What's going to happen? I need more hardware. I need more compute power in the background. And serverless architecture, when you have stateless systems, it's easy. Not easy, not trivial, but it's easier than when you have stateful architecture. When your systems have state that store, it's very hard to actually get more compute that way. And so I want to talk about how we actually achieve that in Rockset, how we achieve scalability, this autoscale, when we have stateful services. And to do that, I first have to introduce you to the Rockset architecture. And I'll just be brief here. But so we have the first layer here, which is Rockset SQL API, which is just a REST API that we expose to customers and does all the authentication, authorization, permission checks, and so on. Then the second layer we have is a layer of aggregators, which are stateless compute tier, which are executing SQL queries. And finally, the third tier we have is leaves, which are storage leaves, storage nodes that store data locally in RocksDB instances, and data is sharded across many leaves in those RocksDB instances. The writes are all going to this distributed log in the green color, and the leaves are tailing the writes to the log to make sure they're all up to date. Now, what we actually use is not RocksDB. We use this extension of RocksDB called RocksDB Cloud that we at Rockset developed and also open source, so you can find it on GitHub. And what RocksDB Cloud does is it takes SSD files that RocksDB produces, remember they're immutable, and uploads them to the cloud object storage. You can think of it S3, GCS, Minio, Azure storage, and all the others. So as soon as the RocksDB creates a file which is immutable, it uploads it to the cloud. And what that does, it keeps the consistent snapshot of the database in the cloud at all times. And now let's say your new customer comes in, they start to do a lot of queries, or your load increases. What do? What you do is you create a new read replica. You create a new leaf machine, you open a RocksDB Cloud database, and you point RocksDB Cloud database to existing S3 bucket. And then this RocksDB Cloud database copies all the SSD files from the S3 bucket. This is usually very fast because S3 has a great throughput. And you're not disturbing any of the existing replicas that are very busy serving this workload. Because, as we said, we are adding new replica because we are already very busy. We do not want to add yet another load to our poor leaf machines. So we download the data from S3, and we start serving the data. But before that, we have to tail new updates from the log. When we copy the data from S3, we have snapshot of the database that's usually a couple seconds, maybe a couple minutes old. So we subscribe to the updates from the log to make sure that our state is up to date and all the writes are reflected. Once we know that we have caught up, then we register with the aggregator and say, hey, I'm here, I can serve, I can help out, I can serve more queries. And this is how we can achieve scalability even when our system is stateful. This is not an instantaneous process, unfortunately. It takes a couple minutes, but a couple minutes later you have more compute power and you can satisfy a higher load. And finally, in the conclusion, what the three techniques I talked about, schemaless SQL allows us no need to configure any schemas. You can just insert data as it is from wherever it is. Convergence indexing allows us to not have to configure any indexes. And serverless architecture allows us to not have to configure any servers. And we have not built the world's fastest database, but I believe we have built the shortest path to go from data to applications. And the reason we did that is because we believe as soon as you make tools easier to use and you make workflows easier, this catalyzes creativity in your organization. Thank you.
Good talk, thank you.
Thank you.
I got a couple of questions just to clarify the architecture. So, and maybe I missed them, in which case, forgive me. So, one question is, what's in the log? Is it data, or is it stuff like this file was added, this file was removed? And the second question is, what sharding strategy do you use to determine which data goes in which RocksDB instance?
Very good question. So, in the log, all the new updates that are coming in are written to the log first, and then they are tailed by the leaf machines, which then write them to their local RocksDB instances. And the data is sharded in doc-sharded way. So each document lives on exactly one leaf machine, and it's replicated to one or two more.
And is it sharded randomly, or?
It's sharded based on primary ID, primary key ID, and then just sharding function, a hashing function, and a modulo, a number of shards.
I have one. Does your converged indexing make query planning more simple or less simple?
I think so. For query planning, I would say simpler, but we still have to build a full query optimization framework. So we still build full query optimization framework because we need to decide between, selectivity, not selectivity, and so we have very complex rules that we build. They say explore these different query plans and score them, and then choose the best one. So there are some pieces that are more simple, but the framework is still very similar to the existing frameworks that other systems in the query optimization have.
Hi, thank you, Igor. So I guess I have two questions on the schemaless side,
Mhm.
did you look at any of the research on dependent typing out of Idris, anything like that, to think about how to handle that? It looks like there's probably some efficiencies that could be gained by looking at some of the stuff that's coming out of the FP world.
Sorry, which world? I'm actually not familiar
Oh, the
with
functional programming world?
Okay.
So Idris is an offshoot of Haskell or a flavor of Haskell, has dependent typing. So if you think about like how you would express a SQL table that had a heterogeneous set of tuple types, it would be a union type of those, right?
Oh, I see.
And how do you think about like, breaking up a union type bucket, and what are some efficiencies that could be gained? So I guess that's my first question. The second question was in this in using RocksDB, like writing 3 sets of data. Did you explore using R-tree indexes at all instead of using that to fit a tree-based model?
That's actually the second question. So first question, I'm unfortunately not aware of that research. I would be very happy to talk. I think we have time in office hours to talk a bit more about that. For the second question, it's actually a very good question of R-tree indexes. And what we have explored R-tree indexes, not yet built, is range queries on numeric types. So if you have numeric types in your data set, search indexes are usually quite bad for that, for some deeply technical reasons. And what we actually build is we build this multidimensional indexes, and we would like to have the multidimensional indexes where we have index range of values, and right, so values from like 10 to 20, we build one index for those, and then range from 20 to 30, we build another index for those. And this is where we explore building R-tree indexes or any kind of range indexing. But what we did is we built a static indexing for those. So we build static ranges, and then if your value falls into the static range, then we index in that range. And I would like to build R-trees, but it's kind of hard to integrate those well with RocksDB. I think at some point we will have to, and we will. But so far we have static range indexing that kind of serves the purpose of R-trees in our system, but it's not as good as R-trees themselves.
I gave a talk about this last year,
Oh, really?
and the solution I advocate is create a use a space filling curve, like a Hilbert curve,
Yeah,
and index that.
that's what we do.
Then you can use a one-dimensional index rather than going to the effort of building R-trees, which are difficult to manage.
So that's exactly what we do. And for locations, we do space filling curves. We actually use Google's S2 library. And then, yeah, we use RocksDB, which is a single dimensional index. But I don't know, I have not actually explored whether building R-trees within RocksDB would be better than using RocksDB themselves as a one-dimensional index. But so far, yes, we're doing this as one-dimensional index because it's easier, that's for sure.
Question. So it sounds like from the talk that this is append only. Is that correct?
No, this is, so because we have RocksDB as an, sorry, I did not talk much about RocksDB itself in terms of the capabilities we provide, but we use RocksDB, which supports, read, modify, writes, deletes. So we do support basically any kind of writes to the database.
Cool. Yeah, that was
Yeah.
just my question.
Yeah,
Thanks.
thank you.